What's up, guys? It's Lorenzo, and welcome to Physics on Lab number 4. So the purpose of this lab is to observe the motion of a spring mass system, where the mass swings through an arc and oscillates on a spring at the same time. Now, the principles that we're observing here, the principles of motion, are the energy and momentum principle. And just as a preview, the results I found today is that the change in total energy of the system oscillates around zero, and there were differences between my experimental data and the model I created. Now here we go. We have a couple formulas here. We have the oscillation period formula. We've got momentum formula. We've got the formulas for energy conservation and kinetic and potential energy, the force of a spring, the force of gravity. So all of these we're going to use, as you can see written here, we're going to use these throughout. And actually, let me slide into presentation mode. There we go. Very good. So our initial conditions include the system being the spring mass at the end of the spring in the Earth. The surroundings are negligent, therefore the work done by the environment is zero, and the heat transfer by the environment is also zero. That's your W and Q. Your time was 1/10.5 seconds, which is 0.95 seconds. The mass is 0.4202 kilograms. Your initial position marked here, that's just from the tracker. Initial velocity, of course, is zero. So I'm going to first show you the video and in the markings I received from tracker. Obviously, I made a slight mistake at the beginning, but I got a really good chunk of the data here. As you can see, I actually logged about 100 points, and we can let this thing go through just for a second. But as you can see here on the right, the center of this circle, as you know, it's going up and down, side to side, harmoniously. It's creating this oscillation you see here on the right. And as it loses energy, this oscillation pattern also diminishes. Let's go on to the data. So as we can see, the data, it's here. And obviously, it just oscillates, as you can see with the graph. I mean, I made the point about the data. Okay. Let's get into the glow script. So here we go. This is all preliminary visualization and graph initialization. Here are the initial conditions I mentioned before. This is for importing the data from tracker. This is the 1/10.5 seconds. Acceleration of gravity, a spring constant, length of the spring. Here we go. I mean, you got it all here. Got these. You had to add the formulas for the different potential and kinetic energies and total energy. We defined initial energies. We've got the force of gravity being the ball, m times a, using a as gravity, m times the mass of the object. This is your spring formula. This is net gravity. I mean, these are all things that you can recognize here. So we went through and just follow the instructions here. But I'll run the program, or I won't run the program. See here that just to save time, this is the result that I achieved. Sadly, this model, while similar, did not accurately depict the motion of the tracker. And here's the error, and I'm explaining it. I definitely believe that it's due to inaccuracies using the tracker web application to mark point masses, and then also when I was importing the data for comparison. But the biggest thing I would think is the possible calculation errors for the values of K and T due to the measurement of, again, my tracker inputs. But let's continue on. Okay, what does it all mean? So for your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. So the energy principle is not satisfied because the total change in energy oscillates around zero, as you can see here in this graph up here. You've got the total energy shown by delta E here. So this is a change in total energy. And also, if you add up the potential and the kinetic energies, it would equal the total energy. So let's say these waves, they basically cancel. There's constriction and interference here all throughout. Basically, it results in this yellow orangey line here. It's oscillating around zero, therefore the energy principle is not satisfied. Also, kinetic energy is negative in some points, and that should not be. Okay, finally, using the data you obtained in a tracker, make two separate assessments of oscillation periods. Okay, here we go. We have an average oscillation period in the X plane, and that was 1.648 seconds per oscillation. And we had an average oscillation period of Y, and that was 1.5504 seconds per oscillation. And the difference between these is 0.1376 seconds. And I decided this difference will manipulate the calculated value for K, and therefore the spring force and also spring potential energy. So that's in the US. And this can be attributed to the different angles at which the mass was released. All right, thank you for your time, and next time.